Good evening, Himanshu. We'll start off in a few minutes. Just got a new writing pad. See if it works well. Okay. We will be doing week 6 of the course. The questions that were covered in the quiz. Okay, that will be done. Okay. So starting off. In this week we covered temporal difference methods and the main focus was on temporal difference method, and other than that there was also Q learning, which is a type of temporal difference method, and TD control and Monte Carlo tree search was covered. Means you can understand that. So we first off started with means we continued from the previous week in the form of the importance sampling. So from the previous week we started off with importance sampling, then moved to uh, means drawing the understanding from the importance sampling. We introduced off policy Monte Carlo, and there we understood the policy that is originally used and policy that is estimated. Okay. So those two things we understood there, and then we came to the rollouts. Okay. And important algorithm under rollouts is UC trees, and leading to Monte Carlo tree search algorithm, and the action selection phase in the Monte Carlo tree search is uh, by upper confidence trees. Okay. Then we came to temporal difference methods. Okay. So so in this question, as you can see, which of the following are true? So dynamic programming is there. Dynamic programming we have covered long before. Okay. And temporal difference method and Monte Carlo methods. Okay. So the so the idea is somewhat like this. In dynamic programming method, we came across uh, problem like this. So you're exploring different so these are the trajectories, okay, and these circles here denote the states that we have reached, okay. Okay, so so in dynamic programming, what you're doing that you're exploring every state here, and after that you are exploring and exploiting the meaningful states more, leading to a convergence. So here what you're doing that you're storing the result of every state. Once what did you achieve in that, uh, so full backup is there of the rewards that you received at every state at and it is bootstrapped, okay. uh, okay Next, in the case of Monte Carlo method, what you're doing is that you are taking samples over a specific direction, okay, and so there is no bootstrapping there, okay. Okay, uh, so let me write it down. So in the case of Monte Carlo, so what you're doing is that you're taking samples in a specific direction, okay, like that, and so you're taking backup of the sample that you have taken, not of the full tree. uh, Sample backup, okay, and so there is no bootstrapping here. So bootstrapping, you understand, in dynamic programming what happens is that well, first you store it. That is the most important component of dynamic programming. Bootstrapping is that when you reach again you update the values, okay, but in Monte Carlo there is no update of the values, so there is no bootstrapping, okay. Next, in temporal difference learning, so TD methods, what happens is that so it is like the shortened form of the Monte Carlo, except that there is bootstrap as well. So you're storing, so you can update the values repeatedly, okay. This is sample backup where the sample is very small, okay, and there is bootstrap, okay. So this is the organization of dynamic programming Monte Carlo and temporal difference method, okay. So in dynamic programming you use full backup and bootstrapping, so that is correct, right? And okay, sample backup and bootstrapping, okay. So this is sample backup and bootstrapping. Is sample backup and no bootstrapping. So ABD is the answer. Space constraint here. Acha. So so here we have got it wrong actually. That Monte Carlo doesn't use full backup, okay, sample backup, okay, and no bootstrapping. So D option is not correct, okay. Answer is A and B. Okay. On to the next question. Any doubt here? No doubts. Okay. So moving on. So so TD0 method uses. So first you have to understand what is TD0 method, right? So coming on to that. So the mathematical formulation is somewhat like this. So so expectation of GT slash ST is equals to S. Okay. So what you're taking is the expectation over return. Okay. And just 1 minute. Okay. So so as I was saying, so this is the expectation. Okay. And the point is that so this expectation you cannot calculate because the return is like increasing, and means like return changes after every state. Okay. And so you take a sample of the return from this expectation, and so so if you can understand uh, this this expression was the start of the value function actually, v pi. Okay. So this is the actual definition of v pi. Okay. This is from which we derived that the expression of the v pi. So you understand that value function is ultimately giving the expected return here. Okay. And okay, and this is from which we got the Bellman equation. Okay. Now the situation is that we do not want to in the temporal difference learning we we do not want to calculate this expectation explicitly, but want to sample this return values. Okay. So say one sample is GT here. Okay. And so what you do now is that, so this was the value function, right? So v new I define as v old, and you are at state S. Okay. And notation. Okay. Plus alpha times GT. Sorry. So so this is alpha times GT minus v old cap S. So what you did here was that uh, you can understand that so v pi here is the value function, okay, which gives the return up to that time, okay, expected return up to that time at a given state s, okay. But the point is that this expectation is not possible to calculate. So what you're trying to do is that to calculate the new v, okay, you're doing old plus alpha times error, okay. So this is the moving average style update rule, okay. So this is the gt, the return that up to that time, okay, and this is the old value function. So you subtract that, that is the error, okay, and you multiply it with the alpha and update the old value function to get the new value function, okay. So this is our formulation here, okay. And moving on, so first this gt can be written as rt plus 1 plus gamma times rt plus 2 dot 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 dot, and this is rt plus 1 plus gamma times gt plus 1, okay. So you can just write it as gt plus 1. Now what you're saying that this is equals to g rt plus 1 plus gamma times g little difficult because like I have taken this new writing pad, little bit of struggle here, okay. uh, and this becomes v cap st plus 1, okay. So what you get from this is that uh, so we are writing the gt plus 1 as approximately v cap st plus 1, okay, at a next state st plus 1, the value function v cap, okay. And okay, so so now the point is that so you can replace the gt, the sample, like this, okay. So okay, so this is our actually approximate state approximation here, okay. In place of gt plus 1 you are writing v cap st plus 1. Next what you have, new slide, and so you write the equation as v new cap st is equals to v old st cap plus alpha times, so you replace gt by this that we found out, rt plus 1 gamma times v old cap st plus 1, okay, minus v old cap st, okay. So this is called the TD0 algorithm, okay, evaluation sample. So this is used for evaluation, okay, and okay, so that is the point. Now moving on to the question, okay. So uses unbiased sample of the return. So so TD0 algorithm is this one, okay, and the question is that it uses current, first I'm going to the option 3 actually, current estimate of the value function, current estimate of the value function. Yes, V old is the current estimate of the value function here, so it is using V old here. Okay, so current estimate of the value function is correct. Okay, okay. TD0 method uses a sample of the reward. Acha, oh, last time. So you are able to hear? Like I got my headphone off actually. You are able to hear? Thanks. So you have written something. Actually, I got my headphone off. Sorry. Okay. So let's continue. So the point is that TD0 method here, as you can see, uses the old V old here. Okay. So that is the current estimate of the value function. Okay. Next. So TD0 method is a sample of the reward from the distribution of the reward. Yes. So as you know that we have taken a sample of the reward here. Okay. Or this is a return, right? But like in the final equation you can see this is the sample of the reward. Okay, so we are using that. Okay, this is also correct. So TD0 method uses unbiased sample of the return. So this is the return. Okay, that we have used. So is it an unbiased sample? Actually it is actually not unbiased. Okay, so gamma, so it would be unbiased if gamma is equals to or like in some way related to the number of rewards that are there, but gamma is usually taken as a constant discount. Okay, so this is a biased sample of the return. Okay, not unbiased. Okay, so this one is wrong. Okay, next, any doubt here? Okay, moving to the next question. So this is SARSA algorithm. So let me show you what that is. Okay, so then we'll move on. Uh, so before SARSA, let me show you what is TD0 control algo. So what we do is that in the case of TD0 control algorithm, what we are doing is that we are using Q in place of V. Okay, so Q new, so the same formulation just with a Q here. So Q new is equals to Q old STAT plus alpha times RT RT plus 1 plus gamma Q old S T plus 1 A T plus 1 plus minus Q old S T A T. Okay, this is our formulation. So actually the same thing, just replacing V with Q. Okay, uh, so this is the thing. Okay, so this is the TD control algorithm, and So in this what you have is that you will do an epsilon greedy exploration, okay, and so in this the 80 that you're using here, okay, so you can see that in the case of that TD algorithm we did not have any 80, okay, only state was the important factor, but here you also have 80 here, okay. So so what you do that as you pick an action 80 and then take the queue with the epsilon greedy approach, okay, then update this queue but don't update the 80, okay, keep the 80 same, okay, okay, till convergence, okay. Okay, so then this algorithm is called the Sarsa algorithm, okay, and so if you don't take a new 80 here, okay, so then what is so then it is a on policy algorithm, okay, and if you take any 80 for this algorithm, then it is a off policy, okay. So but in Sarsa what you're doing is you're not taking a new 80, no, new 80 means new action, so it is a off no, it is a on policy algorithm, okay. So this one is wrong and it is a TD method, so it is a TD method, that is correct, okay. TD control, actually it uses bootstrapping to approximate full return. Bootstrapping, uh, so so first that you can see that last option is wrong because you're using epsilon greedy. You cannot be a complete greedy approach, and then the convergence is never possible, okay. uh, okay, and so it uses bootstrapping to approximate full return. So to understand this, so bootstrapping, you can understand that it is updating the queue repeatedly, okay, so that is correct, okay. So as you can see, the queue new, we are once you calculating the queue at every time step, okay, uh, uh, okay, repeatedly to get to the better queue, okay. So it is a bootstrapping method here, okay. So this is correct, okay. Any issues, any doubt now? No doubts, okay. Okay, let's continue. So in expected Sarsa, we may select actions of policy. So now the from Sarsa, which is a on policy concept, we move to expected Sarsa, which is a off policy concept. So what is expected Sarsa here? So this is Q S T A T equals to Q S T, sorry, Johnny. Okay. So the expected SARSA formulation is so here as you can see you're using the policy uh, in the uh, in the update rule, so which means that the policy that we are using has to be known, okay, and that is why it is a off policy method. But because in the SARSA it was on policy because we were updating the Q values while the policy was going on, okay, while we were estimating the states and actions and everything, you are updating the Q values. But here you already know the policy and then you are updating the Q values, okay. So that is why it is a off policy method, means the policy is not running while you are updating, okay. So it is a off policy method, so assertion is true here, okay. Reason: in the update rule for expected SARSA we use the estimated expected value of the next state under the policy pi. So what you're seeing is that we use the estimated expected value for the next state under the policy pi rather than directly using the estimated value of the next state that is sampled on policy, okay. So estimated expected value of the next state under the policy pi. So under the policy pi, so you are taking the expectation, which is the summation, and under the policy. So next state is st plus 1, of course, okay, and rather than directly using the estimated value of the next state that is sampled on policy. So we are not directly using the estimated value of the next state, okay. So if you compare with the previous one, yes, so in the previous one we are just using it directly, the estimated value of the next state, but here what you're doing is that you're taking expected value over this new state of Q, okay. So that is what is written. So that is why it is a off policy. So reason and assertion both are correct actually. Answer is this, A. Any doubt here? No doubt, right? So let's move on. So next we move on to Q learning, okay. So I will introduce what is Q learning here. Okay, so let me explain. Okay, so Q star STAT. So Q star here defines the optimal Q for the state st and action at. So that is written as expected value of rt plus 1 plus gamma times v star st plus 1. Okay. Okay, so if you can remember this here we've used a similar formulation, but you can see that we are not calculating the optimal return here, but just the return for that state at that time. Okay, so this was replaced with a v cap st plus 1. So it was not optimal, but in this case it is optimal. Okay, so for getting the optimal q, you replace in the expectation so you can understand this was rt plus 1 plus gamma times rt plus 2 plus gamma squared times rt plus 3, like that. So you can write it as the v star as so rest of the things you can write it as v star st plus 1. So how does it happen is that so if you remember that v star is equals to expectation of gt over st equals to s. Okay, now gt is what is rt plus 1 plus gamma times rt plus 2 plus gamma squared times rt plus 3 dot 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 dot. Now what we are doing is that we're keeping rt plus 1 intact, okay, and taking partial expectation over this. Okay, now what does this become is v star at a later state st plus 1. Okay, so that is what you can see. Okay, so that is how we got q star. Okay, this is actually from the Bellman equation. Okay, now what we do is we can write this as expectation of rt plus 1 plus gamma times max of a dash over action a dash q star st plus 1 a dash. Okay, so you can write a v star, a optimal v, as maximum over a dash. So this is also from the Bellman equation. Okay, so this is the q star st at. Okay, okay, now so you've got the optimal q star at st and at. Okay, now you want to find out the so as you can see here for when you're taking the expectation over a dash here, so you can get the optimal here. Okay, so in the case of q learning, you're replacing here with the optimal q star here. So that is what we're going to do now. For the update rule, stat is equals to okay. So we have calculated the expression for the optimal q star at a st comma at. Now what we're going to do is that we're going to calculate the update rule for q. So that is going to be Okay, so this is going to be STAT, and okay, so new old is there. Okay, so this is new, this is old, plus A times RT plus 1 plus gamma times or mu times max of A dash Q star ST plus 1 A dash minus Q ST AT. This is the old one. So this is our Q learning algorithm, and so the difference you can see is that in case of Q learning, you're taking the optimal Q here, okay, and in the case of TD0 control, or you can say that we call it SARS algorithm, you are taking a safe estimate, okay, using the expectation, okay, but given the number of samples up to that point of A dash, okay, and in the case of Q learning, you're taking the optimal Q at that state and for that action, okay. So so this is our question here. Q learning can use asynchronous samples from different policies to update Q. So so it is true actually, and why you can take it, because the update rule is not dependent on the subsequent queues, okay, it is dependent on the optimal queue, okay. So it can take different policies to update queue, but it will still converge, okay. So Q learning is a off policy learning algorithm, and that is also correct, and that is actually the correct explanation as well, because you already know the optimal, okay, and then you are using, okay, not while the policy is going on, okay. So answer is 6A. Okay, any doubt here? No doubt, right? Okay, moving on to the next problem. So you have a two-player game here, and so we have modeled that as an MDP. Instead of learning a policy over the MDP directly, we separate the deterministic and stochastic result of the playing an action to create an after state as discussed in the lecture. Consider the following. The set of states that make up after states may be different from the original set of states for the MDP. Okay. Uh, so what you're doing is that so we take the example of the tic-tac-toe game, okay. So cross and zero. So suppose the zero cross was there from the start, and you took the zero, okay. The action that you could take was deterministic, but you've already taken the action, okay, zero, okay. Now the action which the opponent takes is stochastic, okay, can be x here as well, x here as well, okay. So that is our point. So we're removing the deterministic part after taking the deterministic move, and keeping the stochastic part of the game intact, okay. So that is what is called after states, okay. And so the set of the states that make up after state may be different from the original set of states for the MDP. The original set of states can be different, okay. Means original state, you took that zero. Before that, you can take zero at different points, but after you took that step, okay, then the set of states are that where the x will lie, okay. So that is different, okay. So one is correct, okay. The set of after states could be smaller than the original set of states for the MDP. Uh, so as you took the zero here, okay, So number of spaces left to take the cross has reduced. Okay, so it can be smaller. Okay, so that is also correct. So both of these are correct. 7 C. Any doubt? Any doubt here? No doubt, right? So moving on, the next problem is this. Okay, so rollout algorithm take advantage of the policy improvement property. Rollout algorithm selects actions with the highest estimated values. Okay, so rollout algorithm, what does it mean is that the the policy uh, that will perform for our problem, we are using a in place of that policy, or using a heuristic to solve the problem. And so that is why it is called rollout. You're simplifying the policy and taking a heuristic set of steps to achieve the objective. Okay, uh, so the policy improvement property. So what does it mean actually? Let me explain. So in this you are taking the so in this you're taking the actions such that the uh, so the point is that if the problem has inherently more variability, then you cannot take too many actions. Okay, and and so so you have to take means so if the variability is more, you have to explore more. Okay, and so the rollout algorithm has to change accordingly. Okay, so so what you're doing is that you're doing the policy improvements property, and so so highest estimated values it is taking. So one of the rollout algorithms is this UCTs. Okay, so what happens is that you're not exploring too much. Okay, but in case the variability is more, you're still exploring uh, the situation that is required. So both of these are correct actually. Assertion and reason both are correct. Okay, moving on. So in the case of Q learning and that's SARSA, so SARSA takes a optimal safer path. Okay, but the Q learning takes the optimal path, which is also can be risky. And in the case of simulated I mean simulated environment, what can happen is that the Q learning can take can cause disasters and the problem may fail. Okay, but the so SARSA is the safer path. Okay, so SARSA is the safer path, and Q learning provides the optimal path, but it can also cause disasters in simulated models. Okay, and that is why in robotics you mostly use SARSA, not Q learning. Okay, and so Q learning is A, and SARSA is D. Okay, so and I have explained why Q learning takes the optimal path, because it takes the optimal Q for update rule. Okay, and SARSA takes the subsequent Q values for update. Okay, next what we have here is that Mm. Which of the following are true for TD0? So the TD algorithm follows the Markov property. That is one important assumption because uh, so as you can see, it goes from one state to another, but doesn't worry about other states. Okay, it only saves those two states, and that is what is called the backup. Okay, and the sample backups, and updates those two state. So that is why it is the uh, that is why the bootstrapping part comes. Okay, so it is bootstrapping and it's sample backup. Okay, but only for two states. Okay, it uses the full return to update the values of the states. So let's bring out the TD0 algorithm where we have written here. This is the one. Yeah, so if I can take a screenshot or something. Okay, so this is your TD0 algorithm written below. So it uses the full return to update the value of the state. Does it use the full return? No. So both TD0 and Monte Carlo policy evaluation converge to the same function given infinite number of samples. Okay, this one is correct. This B part becomes automatically wrong. Okay, why do they converge to the same value function? So important thing is to understand here is that uh, TD0 follows the Markovian property and it makes accurate estimation between two states, but on a larger scale it may fail. Okay, given the small number of samples, but if large number of samples are given, the TD0 works as good as Monte Carlo policy evaluation. So error is given by this. This is wrong. Okay, error in this full part. Okay, and it uses full return to update the value of the states. That's not correct. Okay, so C is the only correct option. Next we have missed some question here, I think. 1 2 3 3 is missed, right? Let's go to question number 3 here. So this is our question here. Answer you can already see. Okay, so this is our question, and we got to solve it. So given gamma is equals to 1 and learning rate equals to alpha, so what does it become? So again we have to get to this equation. Again take a screenshot here. put it here, control V. And now the point is that alpha is equals to 1, gamma is equals to 1. So what does it become? So this is what it becomes. This will cancel out, okay. And what this becomes is RT plus 1 plus gamma is 1. So V old gamma ST plus 1. This is our update rule now. V new ST, okay. Now so for that we so VA is equals to 4 first of all, then V, so we are going from the end towards the right one. So VB is equals to 2 plus VA, that is 4, it is 6. VA is equals to here 5 plus 6 is 11, okay. And okay, VB here becomes 2 plus 11 13. VA becomes so towards the end we get the latest states, right? So we got to focus there, okay. And so that is what is important, means the states gets updated, right, for every value. And so what I write is that VA is equals to 3 plus VB, then VB is equals to 2 plus VA, okay. VA is equals to 5 plus VB, VB is equals to 2 plus VA, VA equals to 4. So VA equals to 4, that is correct, okay. So only one option is there, so this got to be the answer. But VB is equals to 4 plus 2. This question I will see how to do it, currently. Okay, okay everyone, this is the end for today, okay. Any doubt? Okay, thank you everyone. We finish off here if you have no doubts. Okay, thank you.